Hello, my name is Akshat Tangsale, and you're watching the lecture on Introduction to Process Simulation. And in this lecture, we are going to talk about design specifications and equation-oriented modeling. The learning outcomes are same as last couple of lectures. We've had to convert physical units into simulation units, identify the parameters that must be identified for the calculation. We need to draw the process flow diagram and optimize the process to meet design specification, which is the one we are going to cover today. Test the convergence and verify it, and use simple user-defined models like Excel and Fortran and link it to the calculator block in Aspen Plus. For the last part, for the calculator block, you can refer to the video link given here, and it's also in your lecture notes. So the equation-oriented modeling is an alternative strategy for solving the flow sheet in Aspen Plus. We have briefly talked about equation-oriented modeling when I was introducing the process simulation in Aspen earlier. The effectiveness of equation-oriented modeling is best when we are trying to optimize a process or solve a process which has been highly heat integrated or has many recycle loops or nested recycle loops, like the example given here, where the mixer 1 has got a flow going into flash, which then goes back into flash, second flash, and then recycle. And then you can see the recycle loops are kind of crossing over. So um, this will have multiple tear streams when solving the sequential modular approach and can give some convergence problems, whereas equation oriented modeling solves it in simultaneous equation and therefore gives you a better chance of converging this. We can also use this for model tuning or parameter estimation or data reconciliation. So model tuning is when you have an existing model or existing plant where you need to do some tuning. Parameter estimation is also for model tuning but gives you some extra degrees of freedom. And data reconciliation is again trying to optimize existing plant operation to get more profits or something for the process. So the way to model a process in Aspen Plus is very similar to the sequential modeler approach. The initial steps are the same. The sequential modeler approach and the equation-oriented modeling approach are the strategies for solving the simulation once we have set up the flow sheet. The input required for sequential modeler approach and the equation-oriented modeling approach are kind of similar for both of them, except the equation-oriented modeling approach requires a few more inputs. We need to learn about the attributes of variables, and therefore we'll need to in the future learn how to change those attributes of variables, including their specifications. So I'll talk about what the attributes of variables are and what the specifications of the variables are in a few slides time. We'll need to then connect those variables and define our new equations which the equation oriented modeling will solve. We may have to define an objective function for optimization problems. Equation-oriented modeling approach works well when there is an existing solution which is close to the desired solution. Therefore, in other words, it means that we need a good estimation. So it's always good to solve a flow sheet using sequential modeler approach first, which is called as initialization. And then when we switch to the EO mode, the EO mode synchronizes the solution with the SM mode and gets the first guess, I guess, and then uses that initial estimation of the solution to then solve the problem the way you want it to. The sequential modeler approach works only in one mode of operation. It has simulation mode, which is the default mode which you have been using so far in Aspen Plus. The model inputs and parameters are fixed and has no degrees of freedom. The choice of the variables that are specified in the input form determines which variables are fixed. So, for example, if you enter the temperature and pressure of the stream, then those parameters are fixed because that's user input. The parameters that we do not specify are the ones then the sequential modeler approach will calculate for. So those are called as the the calculated values, and the user input parameters are the fixed or the constant values. The EO modeling approach, on the other hand, has got 4 different modes of operation. Most often you're going to use only the simulation approach again in Aspen Plus, and in this lecture I'm going to only cover the simulation approach. This mode is a prediction mode and has again no degrees of freedom, similar to the SM approach. For a given feed condition and operating parameters, it computes the solution for the products. Whereas parameter estimation is a model tuning mode, has no degrees of freedom again, but inputs and certain outputs are fixed and the model parameters are computed. It requires one measured variable. So this is the attribute of a variable for each estimated parameter. Reconciliation mode also is for model tuning. It typically minimizes the weighted least square objective function. So we need to define an objective function, and then the model reconciliation will minimize the weighted least square objective function deviation between the model predictions and some plant measurements. So you need to have data from an existing plant to minimize the solution again. So what I'm trying to say is you're going to model an existing plant and try and predict the behavior of an existing plant using the reconciliation method. So this mode can have many degrees of freedom. Optimization. In this mode, usually you have again some operating conditions from plant. Those are given as set points, and you want to then maximize or change those set points so that you can maximize the profit, and therefore again you have many degrees of freedom here. The fundamental difference between all 4 modes of operation is the way the variables are treated. So now I'm going to define what those specifications of the variables are and what the attributes of the variables are. So the status of the variable can either be fixed, free, or have degrees of freedom. So these are the attributes of the variable. When the variable is fixed, the solver cannot change the variable value. For example, for a feed stream, you might have given the temperature of the stream. Aspen cannot change that temperature until you do design specification or something like that, which we will cover in a few minutes. But in a normal solution, Aspen Plus cannot change the value which a user has input. For example, temperature, pressure, flow rates, and so on, for which we have given the value. So those values are fixed. The free values are the ones which solver calculates. So for example, you may have a reactor, a Gibbs reactor, for example, or Gibbs. You have a feed stream coming into the reactor, and the Gibbs reactor estimates what will be the product stream flow rate and the component flow rates. So those are all calculated values depending upon the Gibbs minimization of the problem, including all the reaction equations that the reactor is trying to model. So the solver determines the value of those variables from calculation. Degree of freedom is an attribute of a variable when the solver is free to move the variable to adjust an objective function. So therefore, of course, there must be an objective function for which the variable is trying to have multiple values or have degree of freedom. So the Aspen Plus can move the value of that variable. So any value that we enter at the start of a simulation is treated as an initial guess, and then Aspen can then change those values depending upon how it wants to minimize the the weighted square function of the objective function. The variable specification is the attribute of the equation oriented programming variable. So it is one word description of the variable status in each mode. So for example, let's look at the simulation mode, which is the most common mode. We have calculated specification or constant specification. So when the specification is calculated, the variable attribute is free, which means Aspen is free to calculate the value, whereas when the specification is constant, the value is fixed. That's a user input value. That's the same attribute for all other modes as well. So for parameter estimation, reconciliation, and optimization, again, calculated and constant value attributes are the same. So these are Aspen defaults. When we open the simulation in the sequential modeler approach first and then switch to EO mode, we have only two attributes, either calculated or constant. We can, if we want, we can change those attributes to measured, parameterized, optimized, reconciled, or independent, depending upon the type of the problem we want to solve. As you can see, in simulation approach, the measured and the calculated values are treated as free, and all others are treated as fixed values. In parameter estimation, calculated and parameterized values are free and all others are fixed, and so on. So the first two, simulation and parameter estimation, as you can see, there are no degree of freedom variables here, whereas reconciliation and optimization have got degree of freedom variables depending upon the specification of the variable that we give. However, we cannot just arbitrarily set any variable to fixed or measured or optimized and so on. These attributes have to be well defined so that the net specification of the problem remains 0. What that means is, if you use the equation net specification equal to number of variables minus number of equations minus number of fixed variables minus number of degree of freedom variables, the net should be equal to 0. If the net is 0, then and there are no degree of freedom variables, then the problem is square, which means all variables are either constant or calculated, which I said earlier. So that's the default system in both SM and EO simulation model. And the solution can be attempted using nonlinear equation solution, such as Newton method or Wenkstein method and so on. However, if there are degree of freedom variables and still the net specification is 0, then the Aspen solver will try to minimize or maximize an objective function. So we define objective function right at the beginning in the first week of the lectures. If you are still not sure what an objective function is, you should go back and listen to the recording of that lecture. If the net specification is more than 0, which means a positive value, then the problem is underdefined, which means you have more variables than the number of equations, and therefore it can have many solutions. If the net specification is less than 0, it means you have fewer variables and more equations, then there are no solutions. This problem is overspecified. So either net specification of plus 0, more than 0 or less than 0, the problem is either underspecified or overspecified, and this will result in an error message in Aspen Plus, and it will not attempt to solve the problem. Right at the beginning, it will give you an error. Since the SM approach is used to initialize EO solution, so you would have set up a flow sheet, you would have run it once in sequential modeler approach and then switch to EO mode. The error can only happen if you change the attributes of the variables or the specification of the variables, right? So when you're changing the specification of the variable, we need to keep in mind that the net specification does not change from 0. If it does, if you have changed more variables than you should have, then the EO solver will give you an error message. In both SM and EO solution, we have the desirable variables either constant or calculated. We can switch between the two in both SM and EO modes. So we can, for example, make a constant variable a calculated variable if we want. In SM mode, the way to do that is to create a design spec. So we will look at a problem very soon, but just to be clear, the way to change the attribute of a variable from constant to calculated or vice versa in SM mode is to use a design spec. However, when introducing a design spec, it often introduces an additional convergence loop. So you already had a convergence loop. Let's say there was a recycle, so it would have created a tear stream, and you had that for a recycle loop. But if you introduce a design spec, it introduces another convergence loop, which means another solver, which will try to do the recycle solver and the design spec solver together. So we are now introducing additional complexity in the solution. And when there are nested loops in the solution, SM approach might fail to converge to a solution. However, we can still switch to EO mode as long as we have initialized the problem. Whether or not the solution is fully solved, we can switch to EO mode. In the EO mode, we can change the attribute of the variables directly using what is called a spec group. So the spec group can be found when we click on equation oriented tab, and then on the left hand corner we have spec groups on the top menu. Aspen Plus, as you know, just a reminder again, it requires the net specification to remain unchanged within the spec group for all solution modes to ensure that the problem remains well defined. So here's an example. In this example, we are going to recover acetone from a mixture of water and acetone using MIBK as a solvent. So this is a liquid-liquid extraction problem. In reality, you could just do one block, which is the extract block in Aspen Plus. However, in this case, um, to show the nested loop, I have created a three-stage liquid-liquid extraction problem in which the feed is mixed with a recycle stream coming from a decanter. So you can see the first stage, the feed comes in and is mixed with lighter component stream from the second stage, and the mixed stream goes into a decanter where the product extract comes out, and the heavier liquid product goes into another mixer where it is mixed with the lighter liquid stream from the third stage, and so on. So it's a counter current liquid extraction system with three stages. The question asks you, what is the minimum MIBK flow rate needed to achieve the final raffinate composition below 5 weight percent acetone? In other words, we have to reduce the acetone composition from 50 weight percent in the feed to 5 weight percent in the final raffinate. We will look at a sequential modular approach first before moving on to the EO mode, because that's how you will have to set up in the first place. So let's have a look at the solution. So I've created already the entered the components, and then we select a proper method. So NRTL method will be useful in this case because we have a two liquid problem, and we click on NRTL binary interaction form to download all the binary interaction parameters. Now we can start putting our flow sheet together, and I'm just going to add the blocks first and then connect all the streams together to match with the problem as specified. So we had three mixers and three decanters, and then the feed stream will be coming into the first mixer block rather, and then it will be connected to the decanter. So I'm just adjusting the orientation of all these blocks. So we first add the feed stream to first mixer, then connect the outlet of the mixer to the decanter. Now here you have to be careful which liquid you choose. So I'm going to choose the first liquid as the extract and the second liquid as my raffinate. So raffinate will be rich in water and extract will be rich in MIBK. Now the stream from the second mixer goes into the second decanter, and again the second liquid is then sent to the third stage. So it will go to the mixer of the third stage, whereas the first liquid will go into the first stage because it's going in the counter current direction. Now for the third stage, the second stream will be the raffinate stream, and the first liquid will be going into the second stage. So this is the second liquid, which will be our raffinate product stream, and the mixer will be then connected to the decanter. And finally, the third stage mixer will be connected to the feed stream of MIBK. So now we have joined all the loops. We can rearrange the streams so that they are well aligned. We can relabel the stream names as required. So you can have a look at the problem statement to see what labels I have used, and then pause here and you can do that on your own time. I'm not going to label all of them right away. Only the terminal ones are important, so just labeling the terminal flows for now. Okay, so now we can start entering the information. Since the liquid-liquid extraction problem is normally done at room temperature and atmospheric pressure, we're just going to stick to the temperatures 30 degrees Celsius and 1 bar pressure. The mass flow rate is 1000 kilogram per hour for the total, and the composition is 0.5 for each of acetone and water. We can leave the pressure drop for decanters as 0, and the temperature will be 30 degrees Celsius. Here we can identify the second liquid phase, which should be rich in water. For other decanters, we don't need to specify because they are now automatically defined by the first decanter that the second liquid is rich in water. Okay, we've specified all the minimum input parameters. We haven't done the stream value for MIBK, so let's enter that. So 30 degrees Celsius and 1 bar pressure again. And we don't know the mass flow rate yet, but for initializing the problem, that's the minimum required input. So we will have to enter some value. So I'm just going to assume 500 kilogram per hour for now. And then let's see what solution it gives us. So the input is now complete. We can run the simulation in SM mode and have a look at the stream summary. So the default stream summary does not give us the composition, so we have to create a custom stream table and add mass composition, mass fraction to a custom stream table. So as you can see, the raffinate stream contains about 11%, 11.66% of acetone. So it does not quite meet the desired specification of 5-8%. Our choice is to either manually increase the MIBK flow rate and see how it changes. Alternatively, we can just use design specification. So here we can go into flow sheeting options and design spec, create a new design spec, and define a new variable. So I'm going to call acetone as the new variable, and we want to control the stream composition. So select a stream category and then look up mass frac for the mass fraction, and the stream we want is raffinate and the component we want is acetone. So that defines the variable. We need to enter the specification that we want. So right click on the spec and then drag the variable that we want. So it defines the variable that we want to control. The target is 0.05, which is 58%, and the tolerance we can enter 0.005. Now we need to vary the variable that will control the flow rate. So here we want to control the stream flow rate. So we can go to mass flow as the type, and the stream we want to control is MIBK stream, and the component flow we want to control is MIBK. Here we can enter the two limits, the lower and the upper limit. Remember, the value that we entered earlier should be between those two values. So the lower limit I've entered is 100 and the upper limit I'm entering is 1000. So I can reinitialize and then run this problem, and it converges fine. So we can go back to our custom stream table and have a look here. The acetone composition is now below 58%. It's 0.054, and the MIBK flow rate needed is 856.86 kilogram per hour, which is above the 500 kilogram per hour value that we entered. And in the stream, in the design spec results, you can see all of that summarized. And if you go to the control panel, you can see that there are two solvers. One solver is for the recycle loops, and the other solver is for the design spec. And if you scroll down, you should be able to see the number of iterations it has taken. So it needed 14 iterations to solve the tear stream, which was S5, to converge this solution. So that is how you would use design specification to change the attribute of the variable. In this case, the MIBK flow rate was constant at the start when we entered the value of 500 kilogram per hour, and then we change constant to calculated value using a design spec. Now, before we go to the EO approach, we need to look at how to identify the variables that we want to change the attributes of. To identify the EO variables, there is a format which Aspen uses to name the variables, and the format is block id dot variable id dot description, where the block id is the block name including the hierarchy names if appropriate, and the variable id is normally blk, indicating that the variable is within the block. So for example, if the block is b1 and the stream coming out of the block is s1, then the block id dot variable id will be b1 dot blk s1, and the description is a short description of the variable. For example, it might be the temperature of that stream, so it could be b1.blks1.temp, and so on. So these variables you can have a look in the examples I'm going to show you in the following slide, in the video I mean. Since in this case we want to specify the composition of acetone in the raffinate phase, and the composition must be 0.05. If we look at the variable IDs, which I'll show you in a minute, the variable IDs are in mole composition. They are not in mass composition. So we need to first calculate what is the mole composition of acetone. Now, to convert the mass composition into mole composition, we can't just use one value, that is 0.05, because to convert from mass fraction to mole fraction, we need to know composition of all three components. So what we can do is we can use the SM approach solution to have a look at the mole composition. So if you look at the solution of the SM approach, the mass fraction of the raffinate we get is 0.93 of water, 0.045 of acetone, and 0.024 of MIBK. And the mole flow rates are given as well in the stream table. So 23.62 for water, 0.3577 for acetone, and 0.11037 for MIBK. So from here we can calculate the composition of acetone in mole fraction terms, in the raffinate stream, and that is 0.0148, and we can use this value as the target value in the EO modeling approach. So let's have a look at the EO approach. This is the flow sheet that we had created earlier, and we can go and deactivate our design spec and reinitialize the stream so that we have the initial guess value of 500 kilogram per hour for MIBK stream. So now that the stream has reinitialized, we can have a look at the stream table and go to the custom stream table, and you can see we are back to the original value of 11.66 weight% or 0.1166 mass fraction of acetone in the raffinate. So just to be clear, the of the variable IDs, I'm going to rename the blocks. So we want the mixer, the first mixer to be M1, the second stage mixer to be mix 2 for the second stage mixer, and mix 3 for the third stage mixer. Likewise, for the first stage, the decanter we can call decant 1. For the second stage, we're going to call it decant 2. And the third stage we can label decant 3. This will make it a bit easier for us to find the streams, and we can also label the stream numbers. So I'm going to call the heavy stream, the water stream, as L, and the lighter stream as V, and the number L1 is the liquid stream coming from stage 1, and likewise the lighter stream V2 is the one which is coming out of stage 2, and so on. So this is the convention we normally use for separation processes. The stream number is the number of the stage which it is coming out of, and L and V just tells us that it's the liquid stream, and V stands for vapor, but here it's not vapor, it's just liquid, but a lighter liquid. So now that we have labeled all of them, we can check our EO modeling variables. So here, as you can see, mix1 blk dot mix1 dot blk dot feed underscore moles. So that's a variable which tells us that mix1 is the first mixer. BLK tells us that this variable belongs to the block, and feed moles tells us that it's the flow rate of mole flow rate of the feed stream. So feed being the stream that we have defined. Likewise, we can choose any other property, like here number 20, column row number 20, it says mix1 dot blk, so that must be the block mix1, and dot blk is telling us that this variable belongs to the block, and it says dot heat duty, so this must be the heating duty of the mixer, and naturally the heating duty of the mixer is 0, it's adiabatic. You can scroll through these and have a look at the variables to identify what variables are defined, and also check the specification. So either they are calculated or they are constant, as we might expect, because this is a simulation. You can see the run mode is simulation on the top here. So once we have scrolled through the variables, we need to see which variables we can control. So here we have MIBK, block mass variable, that is constant. We want to change that to calculated because we want to calculate the mass flow rate of MIBK. And for the third decanter, we want to find out the composition. So here we have decant 3 dot blk dot raffinate underscore acetone. So that's the composition of acetone in terms of mole in the stream. Now here we have the summary of what composition we want to achieve, which is 0.0148 for the acetone in the raffinate stream coming out of the third stage, or the raffinate stream. So that is the mole composition that we want to enter for the block, the ID that we had looked earlier. So we can go to the spec group and start defining the specifications for the variables that we want to change. So first we can select the decant3.blk.rafnet underscore acetone. So this is the composition. So this was earlier calculated. Now we want to make it constant, and we want to enter the value of 0.01484. The physical type of this is its contents, and the unit is fraction. That you can check in the attributes page, or the EO variables page that we had looked earlier. Now we want to change the flow rate of MIBK. So go to MIBK and look at blk.mass. That's the mass flow rate of the MIBK stream, and we want to make it calculated. It was earlier constant. We don't need to enter the value, of course, because EO will calculate the value of this stream. The physical type is mass flow, and the units are kg per hour. And we can then run this simulation. We get some error here, EO solution failed, it says. So let's go to our control panel and have a look at the error. It says the pressure value of minus 0.32 is outside of the allowed range of 0 to 0.1, and it gives that error for all the blocks and all the streams. And it says that the error is coming from the post solve stage, which means it's not able to check. So instead of giving 0 pressure drop, it's better to enter the actual pressure. So I'm going to create and go back and change the pressure to 1 bar in all the blocks. So EO might have been able to solve the problem, but then while doing the post-solve check, it get an error in pressure balance. So having that 0 might not be giving us the solution. Okay, now that I have changed that, we rerun this problem, and this time the EO solution has converged. And we can go to the stream summary and have a look at the stream raffinate, which gives us 0.054, which is the design specification that we wanted. And you can see the MIBK flow rate is 856.958, which is very close to the SM value that we achieved. And in the control panel, you can see the number of iterations is 0. It solves all the equations simultaneously, and it used very little time to solve this. So these are the statistics for optimization, and the total optimization time it needed 0.02 seconds. And it tells you the objective function value and the objective conversion. So obviously we don't have any objective function here. The residual conversion function had a very small value, which is nearly close to 0, and we did not have any objective conversion function or the objective function value, so all those are 0. So that concludes this lecture. And again, we have a tutorial problem later to give you some hands-on practice to work on a simulation and then enter a design specification in the SM modeling approach, and then you reinitialize it and then run the problem using EO modeling approach. So I hope you enjoyed this lecture, and I'll see you again in the tutorials. Thank you, and bye-bye.